Hello everyone and welcome to FLOSS, our course on open source software and the industry. We are still in the first part about open source in general and in particular now open source and the engineering processes behind it. We talked about intellectual property and the community processes. This time it's engineering processes, next tools, after which we will switch to corporate governance and strategic open sourcing of open source software projects. The engineering part of open source will provide us with a few innovations that we will look at, but mostly we will compare open source software engineering with the best practices we know from regular non-open source software development. So let me recap here some of the thoughts we already had about open source projects. First of all, an open source project has a community open source project has a project community, which includes the people and companies by way of people who are engaged with the software in one way or another. Obviously, software is being developed. That software isn't really a classic product for a market, but it has some of that because it's usually not competitively differentiating software, meaning companies do not compete for that software because otherwise are using that software so much, because otherwise they would not be collaborating in its development. And then those who actually use these open source components being developed as part of open source projects, we have users, which might be individual developers, natural people scratching their itch, as the saying goes, or companies embedding the software in their products. So the open source software is used as part of products or serves some purpose to its users. And I think that means we need to best view open source components as feeding into something, which in more classic economic terms, meaning an open source project is a supplier to various customer or user projects that make use of it. So in this graphic, you can see how a particular open source component not only uses other components of which it's a user and these other components are its suppliers, but actually is being used by closed source products or other open source projects as well. So being a supplier is actually a role that is attributed to a particular open source project. And that has a consequence, which is that open source software projects are best viewed as components, jointly developed or not, but components that have a market, and not just a single user, but a market. So students of my courses know quite well how I make a clear and stringent, important distinction between client-specific projects, where you have a single customer, it's custom development, and products for a market, sometimes also called commercial off-the-shelf software, where there is really a large number or potentially large number of user customers, and hence you need to cater to a market rather than an individual user. And open source components are just that. They usually have more than one user, and as a consequence, more than one party engaging in the project community. Now, the consequence of that is it's not client-specific software development we are interested in, but it's rather product development we are interested in. And the key functions of the development and engineering processes of products for a market are product management, engineering management, software development, and QA, quality assurance, and not so much project management and business analysis, etc., as it would be the case in client-specific software development. So with that in mind, we will be able to review the engineering processes of open source projects much better than without it. So here's another reminder or recap, the roles that people play in open source projects are made up of a 6-stage career path. Here, for bare bones community open source projects that we'll be looking at, only the first 3 are really relevant, being a user or a contributor or a committer to an open source project. And the foundational career stages are discussed later again. So when you look at the classic roles and processes of software development for products for a market, you have product management, engineering management, software development, and quality assurance. And when you try to map the 4 roles, one for each of these process domains as defined in classic software engineering, when you try to map them to the 3 open source engineering roles, which are committer, contributor, and user, you'll see it's all over the place. There is no product manager or single role product manager in open source, nor is there for an engineering manager, nor is there a pure software developer, nor a tester role. It's again committer, contributor, and user, and they all participate by way of the project community in these 4 main key roles, which come with the activities and practices, etc. So when we look at it now, we will see that some of these practice areas, processes are really underdeveloped in open source software development. Specifically, product management basically does not exist in open source projects itself. There is, for example, no strategic product management. There's no market research or going for market opportunity. There is, of course, some of that associated with the companies who might be contributing to open source projects, but then product management really is outside the scope of the open source project. Open source projects may be created because of market research done by some company, but it's not done as part of the open source project. So there is basically no strategic product management in open source projects. Technical product management, so mapping out a product roadmap, writing down product specifications, tracking the progress towards releases, all of that. Somewhat exists in open source, but it's very bare bones and ad hoc. Open source really doesn't do much there. The product specification, if there is any, is typically a to-do list. Let's do this, let's do that. Here's a couple of features that need implementation, and that's basically it. So very, very little, very low key. Engineering management, no. There's a little bit more, but not much. Like with product management, there's really no detailed release planning going on. If there is some, it's often of the kind, if the feature is there and of quality, we'll take it. Otherwise, we don't take it. So if it's there, great. If it's not there, who cares? Well, not quite, but that is the attitude still of most community open source projects. There's also no resource allocation, and that's basically a core property, of course, of open source, because there is no big boss, no engineering manager who could allocate tasks or features to people. So in open source and community open source projects, committers can prod contributors to maybe do this or that feature, but they can't really allocate or assign a task to people. More often than contributors actually pick up the feature or any feature they like to implement and go do it. So it's self-selection. It's not an engineering manager assigning tasks. And that's basically, I have yet to see any structured process for process improvement in open source software projects. People do it, of course, but it's pretty rare and usually, I think, ad hoc. So software development then, that's of course where open source is much more busier. It's very lightweight on any management. Software development is the actual programming, but similar to regular closed source software development. but there's much less planning and feedback as to when people will or are expected to complete the tasks. Quality assurance, that is an interesting topic now. There is a fair bit of quality assurance because people in open source are invested in their project. So much so that sometimes the loyalty of a person is more with an open source project than their employer. In any case, open source performs code review all the time. It's baked into the project structure, into the roles and the distinction of contributor and committer, as we already saw and will see again. Open source these days does a fair bit of automated testing, or at least it has picked up in the Java space, certainly. All the good things about automated testing frameworks from JUnit on to full-blown integration and end-to-end testing. Open source also does a lot, and maybe more so than traditional closed source software development, does a lot of manual testing. After all, you've got these users and they need to be put to good use, so you let the banana, as they say, the green banana, ripe with the user. And because it's free, users are willing to put up with much more than if they were paying for the software. Finally, there's release management that is somehow distributed between product engineering and quality assurance, engineering management and quality assurance. Usually someone a committer picks up the release management job and does it fairly lightweight when compared with traditional software development. So it's really, really interesting how this is different from traditional software development. You could argue that on the one hand, it's embarrassing for open source because there are all these best practices, how to do good product management, how to do good engineering management, and open source ignores it. So these guys, you may argue, have a lot to learn. On the other hand, you could argue, oh wow, there are all these best practices and they apparently don't matter much because open source somehow is able to more or less consistently, with important projects, consistently ship high quality software. So maybe all those best practices don't really matter as much. The truth is probably in between, in that, as always, good people matter much more than processes and tools. Still, I believe that open source actually could benefit a lot by looking more at the best practices of closed source software development and combining them with their own. Certainly in software development itself, where we can observe how a lot of open source software development is still being done on the command line using VI, etc. There are certainly improvements waiting here. So then, what's new in open source software engineering? Well, again, as previously discussed, we can't say there is that single open source process. We only have the principles, the 3-4-5 model of open project communities as discussed in the last session. So we can set up a set of parameters, constraints, if you will, principles that good open source software development adheres to, but not give you a single workflow, a single process model. What is new and interesting and innovative in open source is how it has set up the contribution process, because that is key and centerpiece of software development in open source. How do people make their contributions in such a way that quality is assured and the project moves forward rather than stumbling? Also, I will shortly mention distributed version control. Like the contribution process, it's not necessarily that open source invented all of it, but it's the main popularizer and the main force that made it really work in practice. So the 3-4-5 model we discussed last time, we can say of community processes, including the engineering processes, that they follow the 3 principles of open collaboration, meaning everyone, it's egalitarian, everyone can join and contribute. It's meritocratic. Decisions are made based on the merits of an argument, and it's self-organizing. People choose their processes. We also observed that the 4 best practices of open communication are being followed, meaning open source collaboration, communication is open, which means that it's public, written, complete, and archived with all the benefits discussed last time. And finally, we observed a 5-stage volunteering process of how people join and contribute and lead open source projects. Now on to the new aspects, specifically in engineering, software engineering for open source, and that is how contributions are handled. Contributions to open source software projects can be lots of things. Most notably, of course, it's the source code, but it's also bug reports that you put into an issue tracker or a bug tracker, forum posts you write and answer, the same on mailing lists, even conference presentations that you make to market a particular open source project. These are all valuable contributions cherished by the community of an open source project. But again, of highest importance probably is the actual source code contribution, because that's what the ultimate product is about. So let's take a look at how contributions make it into an open source project's code base. So again, let's be reminded of these roles and the structure they provide to the development process of an open source project specifically. And that is where open source software development is really very different from classic traditional company internal closed source software development. Not everyone who's on the project has change rights, commit rights to the code repository, but rather open source distinguishes contributors from committers. Contributors do not have change rights to the code repository, only committers do. And hence, a contributor has to get a committer to accept their contribution and put it into the code repository. And that's the patch submission or the source code contribution process. So this process, in my observation, has five steps. 5 if the contributor, potential contributor, is smart. Because the first step is not to write code. The first step is to plan the contribution. A smart contributor who wants to make a contribution first looks at the project's current state and tries to align their interests with that of the project. So they may suggest a feature that they want to implement because they need it, or sometimes they simply offer the help and get something suggested to them. But in both cases, the developer, who will play the contributor role here, will think first about what they're going to do and how it could match the project and how the contribution could make it into that project. It's software development, so they have to discuss what it means if they program it the way they want to program it, and if that actually fits the existing code base, doesn't violate any architectural constraints, doesn't upset anyone, because if it does, it may not get accepted. So a contributor thinks hard, explains their intentions, gathers feedback from the existing set of developers, and only then, if all apparent obstacles have been removed, if all risks are understood and are considered manageable, only then will the contributor start to develop the code. So for the sake of the example, let's assume they get this done easily and speedily. So they finish the development of a feature. It works well for them. So then, because they are contributors who do not have commit rights, who doesn't have a commit right, the contributor we are talking about here needs to submit their proposed contribution needs to submit that to the project, typically a particular committer who seems the right person to review and put into place that contribution. So the contributor, all they can do is say, hi, here is my potential contribution. Please review it, and if you're satisfied, please put it into the actual code base. Remember again, contributors do not have change rights. So the code repository, this is critically important for open source projects. They are not free for all. They practice stringent quality control because these projects are important to the existing core developers. Anyway, there are two ways of how a contributor typically submits their contribution. And that is by submitting a patch by email using the command line tools diff and patch, or just diff, and patch will be what the committer does. But more recently these days, contributors will use perhaps pull requests on GitHub or the equivalent form for other forges or distributed version control systems. So we rather than sending email. Now the committer or a committer receives the potential contribution and will pick them up, maybe from a mailing list, and will review that potential contribution. This is likely, unless it's small or very trivial contribution, likely perhaps to be a short back and forth where the committer asks some questions as part of their job now of doing a peer review, a code review, ultimately quality control of what has been submitted. So if the original contributor doesn't answer or answers unsatisfactorily, well, then the potential contribution will not amount to anything. It might just get dropped. There is no right that a committer has to request or make sure the contribution gets into the code base. It's really just an offer, and it might get rejected for poor quality or other reasons. And in fact, patches, code submissions as intended contributions often get dropped, and we'll see that a little bit later. But let's assume in this case the contributor did well and the committer likes what he or she sees, and then in the final step the committer simply commits the proposed change to the code base, making it a real change. Tools will usually track who the original contributor was and who the committer was, so we will see both names in the project history. As I said, there are more or less two ways, both in practical use these days. There's the kind of by hand approach of using command line tools, the command line tools diff and patch. Using diff, developer determines how they change the code of the project to incorporate their suggested changes, and the diff output is then sent to a committer or a mailing list for committers with the relevant information as the diff output, the newly changed, the new source code to be added. The committer then creates a working copy of the project, applies the changes using the patch command, and reviews these changes, perhaps using a visual merge tool or just by trying the source, the project. Many different ways of doing quality assurance here. And if everything is fine, then the committer will commit the changed working copy, which includes now the submission, the contribution by the contributor, and will commit it to the code repository, thereby accepting officially the contribution made by the contributor and putting it into action. This clear distinction between contributor and committer, of course, gets dissolved if it's the same person. These are two roles. So it is possible that a committer, that a developer who is a committer, does also do software development, playing the contributor role, and then short circuits short circuits the quality assurance process by simply putting it into the code repository. For that reason, some open source projects actually require another committer to look at it. So again, it's peer review of code, but clearly not all do that. So here is how it looks like on a command line, how you would use the diff command to determine the differences between two files or two project trees, saving it in what's called a patch file here. When you see the output, you can see how it's textually based, marks the distinction here in addition of the actually a deletion of some source code. And then another person who receives the patch file by email will apply it to their own working copy and then review the resulting new code. A more common way is these days to use, say, GitHub and use the UI for sending out pull requests, which really just tell the contributor sends a pull request to a committer, asking them to pull the changes from their working copy of the repository, the proposed contribution, and then the committer in their own working copy or a branch basically will check out these proposed changes, review them, try the software, test the software, and ultimately, if everything's fine, accept the proposed changes. So it turns out that getting your code into an open source project is easy if you're a committer. It's pretty hard if you're not known to the project. Why would they trust you? And so submissions by contributors, in particular unknown contributors, often don't make it. The work is wasted. It's not that the existing committers deliberately want to waste other people's work. It may just be too much of a hassle. So what could go wrong? Well, a not so smart contributor will not coordinate with the project in advance what they are up to. So it will come as a surprise. It may not fit the project any longer, what have you, all kinds of reasons why the work really doesn't make any sense to be included any longer. The not so smart contributor might simply violate all kinds of practices. There are so many things that need to be considered to make the code right for the open source project, including missing windows during which you have actually only the chance to submit contributions, get them in, like the Linux kernel's infamous merge window. Well, but even if the contributor does everything right, the committer might reject a contribution because the contributor doesn't convince them that the work is good. And you may argue, well, can't they see that the work is good? And the answer to that is yes, if it's a few lines of code, but if it's thousand lines of code, maybe without tests, how would you know? And so you feel as a committer, having the quality and longevity of the project at heart, may feel rather unhappy and unsure about such a lengthy contribution, and may rather decide to tell the contributor that they can't take it because it's just too large. If there's a saving grace, then perhaps the contributor can chop it up, make it a sequence of smaller contributions, which is actually a best practice to get your changes in. Well, and finally, one not too untypical thing that could happen is that nobody has time to take care of the code contribution. One would think everyone's happy for any contribution, but of course people are not. People are busy. So simply any submitted patch, in particular if it comes out of the blue, might just be ignored, rot, and ultimately be unusable because the project moved on and is too different already from that state where the diff was taken for the patch. Okay, so we will now look at three very quite very different projects with very different processes for that reason. And it's the Linux kernel, the PostgreSQL database, and the Tiki Wiki content management system, Groupware software. And the reason why I chose these three is, again, because they are so different, polar opposites on many aspects. Specifically, the Linux kernel is huge. Well, these are all large projects, so none of these is small. I didn't look for different projects here in terms of size because we want well-worn and well-understood processes. But the Linux kernel is unique. As you know, it's an operating systems kernel. It's unique in that it has a fairly strict hierarchy, perhaps stricter than any technical necessity would suggest. But that's historic because it grew out of a single person's work. Quite the opposite with the PostgreSQL database, which has a peer group, a core team of software developers or members of a core team, which who manage the fate of the PostgreSQL database. So no hierarchy, no strict hierarchy here, but rather a peer group. And Tiki, the Tiki Wiki CMS Groupware system, is of particular interest because it's on the extreme of giving people change rights, commit rights to the code repository, because you don't really have to do much to get them. So Tiki is almost anarchic from classic open source perspective, and we will see how that works out in a few slides. So here's the Linux kernel, originally a Unix-derived, Unix-like operating system kernel, obviously very much its own thing, has been for a long time, and it's very important for the industry because as an operating system, every single device out there needs one. And because it's open source and free and high quality, it's widely used. The Linux kernel is really just the core. The Linux operating system is Linux plus all the glue tools and then some. It's GPL version 2 licensed, which is its own unique challenge that we'll address later when we talk about corporate governance of open source. So the Linux kernel is being developed by professionals through and through, all on company time. And that is because of the high economic relevance. Companies invest into the Linux kernel. They want to make sure, because they use it, they need to manage their dependency that their products have on the Linux kernel. And the best way to do that is to be engaged in its development, learn early about the roadmap, and make sure that things fit their architecture. If there are architectural changes, that they know early on what potential problems are waiting for them, and so that they can adjust their products. So lots and lots of businesses and products built on the Linux kernel, and companies need to manage their dependency and investment into the Linux kernel, and they do that by joining development. There are peculiarities next to these general reasons why companies try to get, say, any work they do based on the Linux kernel, try to get it into the Linux kernel. For one, they don't like developing things outside the kernel too much if it means that they have to reapply their changes all the time. So they actually want to get their changes into the Linux kernel to save development costs. On the other hand, and that's a political problem with the whole development process, on the other hand, they often hold back any potential changes because they don't want to show the world, and in particular any competitors, what they're working on too early. For example, USB drivers for any new USB device, if they were to develop it openly, would signal to the competitors of some USB gadget manufacturer what the new USB gadgets are the company is working on. So it's a real challenge that on the one hand, they want to get their stuff merged into the kernel, submitted, contributed, and made it into the Linux kernel as fast as possible, while also not giving away any are not showing any signals to the market what they're working on, because they want to avoid any leaking of strategic information. So, but companies do actively work with the Linux kernel, of course, and as part of the discussion of open source foundations, which will include the Linux Foundation, the host, if you will, of the Linux kernel development. We will review that in a later session. The Linux Foundation is the legal home of the Linux kernel, really an industry association more than a consortium, which has as a goal of furthering the development of the Linux kernel. For example, it employs Linus Torvalds. That's some kind of truce, if you will, between companies, because everyone, of course, would like to employ Linus Torvalds, because then they had the highest wielding power over the kernel, or so one would think. Well, Torvalds, of course, would be more loyal to the project than any company, but things can be very subtle. In any case, all of this was settled by employing Linus Torvalds by a foundation. So no IBM, Red Hat, or Fujitsu employs Linus Torvalds as the person at the helm of the Linux kernel development. As I mentioned already, it's solidly commercial. This figure here, 65%, is very certainly the lower bound. Most likely 100% of the Linux kernel development really is 99.9 is commercial. Linux has been growing steadily. In fact, Android recently overtook in terms of pure numbers on devices, Windows and any other operating system. So Linux today is the most widely used software operating system. So let's look at the core functions of software product development. First, product management. To my knowledge, there is no centralized planning or traditional product management going on in the Linux kernel. The individuals decide what they work on. The community members do collaborate, of course. They talk about what needs to be done, but it's not in the sense of general product management as we know it from products being brought to market, even though, of course, from the companies employing the people who work on the Linux kernel, there's a fair bit of inflow as to where the Linux kernel needs to go. Engineering management, well, the timeline is determined by the person at the helm of it all, Linus Torvalds. All of that is a community process, but ultimately Linus Torvalds can and does decide. The process is a little bit peculiar, if you will. It has changed over time, a couple of times. These days, there's a major release of the kernel every 2 to 3 months, and there's a very well-defined rhythm to it where during release there is basically in the beginning a merge window where new code changes of so-called stable code, I'll come to that in a second, stable code is merged into the main line all the way up to Linus Torvalds, and then the merge window is closed, and the rest of the 3 months from week 3 on to the end of until the release is cut. Basically fixes any problems, fixes are applied, problems are reported, because that is now the most widely applicable testing, and it will, despite all hard work beforehand, unearth more issues. And so at the end of that 2 to 3 month window, the final release for that major release is cut. The so-called stable code that makes it into the main line as part of the first 2 weeks of this release period, the merge window, is actually stabilized outside the main line. So there's a significant quality assurance going on before code submissions make it into the main line and might possibly become part of a release. And to understand that process, we need to look at the hierarchical structure of how code flows through the tree. from the leaves of a tree to the repository at the top, managed by Linus Torvalds himself. So here you can see basically a structured breakdown of the components of the Linux kernel. There's the base code maintained by Linus himself, and then there are the various subsections or subsystems, if you will. One, for example, for networking, one for device drivers, another one for memory management, and so on. And it's a multi-level deep tree or hierarchy, as the device driver base, for example, supports various types of device drivers, for example, SCSI drivers, graphics drivers, USB drivers, etc. And to each of these subsystems, it's all one-to-one mapped from subsystem, topic, to repository, to a particular person responsible for it. So one Greg Hartman, for example, is responsible for the device driver framework or base, which the SCSI drivers and the graphics drivers and the USB drivers are built on, which in turn are managed, the development of which is managed by other people. And all code again flows from the leaves to the root of the tree. So now, if you want to get a patch into the Linux kernel, then here's a short process for how it's done. All of this can be read up on the web. There's a reasonably good description of the Linux development process because many people are interested. So first of all, the design. If someone wants to do something, say, about USB drivers, then they would have to smartly would propose what they want to do and talk with the guy responsible for the USB driver subsystem, etc., etc. So ideally, any design of any not yet implemented feature is done out in the open. So the person who wants to do it describes it, discusses it, etc. And they do their development, and then in stages they have people review it, in particular if it's something of higher complexity. In particular, if it's of higher complexity, it means they need to stage it. So in stages, submit their code. They need to have a big picture, but each patch submission is only small and incremental in that the person, the committer, that it is being submitted to can actually understand and review it and feel good about the review. So there's an early review with a small community or smallish community of people who are really interested in, say, new USB drivers. There's ultimately wider review as it will be put into context to see whether, say, a new driver has any interactions with existing drivers, etc., etc. And it's all, in particular in the case of the Linux kernel, managed through Git as the distributed version control system of choice here. If it makes it all the way to Linus Torvalds, which if things are done right, it will eventually do, then it will be entered into the main line during the merge window. So first on the level of the subsystem maintainer, then these maintainers, that's the committers in Linux terminology, will ask their superior maintainer to pull theirs, and they will pass this on to Torvalds, so it bubbles up the hierarchy. Of course, then it's more and more changes bubbling up the hierarchy. So Linus Torvalds regularly then does not pull small changes like the original submission for one contribution, but the whole boatload of things. So there really is almost no way that this could be consistently reviewed as one large code contribution, which is why it's so more important that this is well prepared and discussed and annotated before it reaches the root of the hierarchy. It means, though, that the higher up in the hierarchy, the ultimately less programming you're doing, you're merging, you're doing quality assurance. And so, for example, Linus Torvalds, who at one point of time probably was the most prolific programmer of the Linux kernel, is now on position 3 or 4 in terms of the total amount of lines of code written, and others are ahead of him. Not that this is a relevant measure for anything. So you can see here how, say, in an example, something about the SCSI driver, some feature needs to be added to the SCSI driver, or some random hacker did that. They probably submit to the responsible maintainer, Dario Belabio here. They submit their patch, perhaps using email. Dario Belabio will review it, in steps have it entered and made it into his repository, ultimately into the main line, forwarded to Greg Hartman, or with a pull request, asking to have it pulled, who will eventually pass it on to Linus Torvalds. So and then that's the basic engineering process, strictly hierarchical, very unique. While there are projects who have copied this model, it's actually not the most common model of how open source software development takes place. The group of peers, the PostgreSQL model, is the more common one. Anyway, back to the Linux kernel. There isn't so much to be said about, well, there is probably a lot to be said, but I don't want to take the time here. They're the basics. You need to stick to the programming guidelines. That would be the obviously most stupid thing to ignore, because your contribution will be rejected right away. It has its peculiarities, if you will. You don't reformat old code, for example, because that would just be wasting time. Yeah, so because of all the interactions, you break your submission into small pieces, make it easily manageable, etc. These are all best practices for how to get your patch in. Quality assurance in the Linux community is community-based in the first step, and then commercial or professional because of the businesses that build on the Linux kernel. So community testing means there's the developer version, the maintainer version, and finally the kernel release. And at each of these stages, there are people who take the software and simply try it. I think there are test suites, but a lot of testing in the Linux kernel is just using it and observing any potential problems. Of interest to the Linux kernel are the businesses built on top of which, who have the highest motivation, if you will, the highest motivation to make sure quality is good and bugs are caught early. And that would be the Linux distributors like SUSE or Red Hat. Now, they have their own internal testing processes. They actually are based on the larger notion of not just taking the kernel, but putting the kernel into the context of a real system, a whole system, which is the Linux distribution. So they will add all kinds of applications, the Apache web server, the Samba file sharing server, etc., and put it together with the Linux kernel, and then run test suites. The intellectual property of these distributors that's unique to them, that's usually not openly shared, the tests of many are, for example, test suites, and they will identify, hopefully, any potential remaining bugs. So the distributors are active in development, they review code, but then they have their own test suites that they use and run against the kernel release to unearth any potential problems. So again, coding guidelines are of course important. The Linux kernel community does use some of the known best practices like code checking tools and not ignoring compiler warnings, but there's probably a fair bit of heuristics, and since I'm not a Linux kernel developer, I'm pretty sure a lot of things are going on that I'm not aware of. All right, so let's move on to the second example, the PostgreSQL relational database system. It been around for a long time, is the leading perhaps open source relational database. For a while it was in competition mostly with MySQL. Now that MySQL somehow is being downgraded by Oracle, maybe it's competing with MariaDB, but really there are just many databases out there now. PostgreSQL is simply a traditional classic enterprise grade open source software relational database system. It's got a large community which supports it. It's permissively licensed, and which is probably one reason for its wide use, commercial wide use. So product management of the PostgreSQL database is done by the core team. So there's a core team of 6 or 7 people. Not all of them are developers. They have a roadmap, and they have a product backlog, but it's very, very lightweight. It's basically a to-do list. Product management does not involve any prioritization, really. People pick the feature they want to work on. So any prioritization of features comes really from the users who perhaps have some need to see the feature in the code base. They do some things like polling the community. So you will see on the website polls, what do you think is more important? And that works because with such an established software, there are always people who are kind of agnostic to what it is they're doing. They're just willing to pick up whatever needs to be done to help the project. The engineering management of PostgreSQL development is rooted again with this core team. It's long-term, stable, 6 people who coordinate releases, who facilitate the consensus building process, but do have ultimate decision power, who hold and administer the major assets like the website, the code repository, etc. There are 20 or something major contributors, committers, in the usual terminology. It's called major contributors for Postgres. These are obviously the people who can commit code to the code base. There are regular contributors who do not have these rights. They have to contribute through these major contributors, that is, the committers. So this is actually a classic project that walks along the lines that I explained earlier. Developers decide that they want to do something. They design their contribution ideally in public so that they gather feedback. Then they submit it. There's a mailing list for that. And this is submitted using the Diff tool. And then patch review takes place by some major contributor, committer, picking up the patch file and reviewing it. And if it works, then it's being committed to the code repository. One particular practice of the PostgreSQL community is the Commitfest. These guys noticed how they were often falling behind in terms of accepting patches, making sure they make it into the code base, thereby losing well-intentioned contributors who would just see their patches linger and get stale. So for that, they invented, or they used, the concept of Commitfest, a particular time frame during which they work through the backlog of outstanding patches, review them, and get them into the code base. They have a software for it where you can see where all the bug fixes, the patches get collected, and how then everyone, or just one person, picks one, works on it, and makes sure it's actually through this process outlined here on the screen. The patch, assuming it's reasonable, makes it into the code base. As every open source any reasonable open source project, they have coding guidelines and patterns of how to program. They use the compiler warnings and code checking tools like any other reasonable open source project. Quality assurance is interesting. Of course, the developers test themselves. The major contributors test again. The release manager tests. Users test all the time. And most importantly, they do have large users which operate Postgres in large data centers who will put new versions to use on for their applications in their data centers to see how the new version performs, and that is quite helpful to find bugs that are really hard to find on a single developer's setup. So these ultimately serve as benchmarks and integration test suites to identify any potential problems. This is the release process. You try to catch up with a Commitfest, have your alpha and beta release, and ultimately the final product release. All right, and now the third process, the somewhat anarchic Tiki Wiki CMS Groupware system. It's got millions of downloads as well, broadly used in active development for over 15 years. And this just has a huge number of features for a wiki or a CMS. Obviously, doesn't even quite know for sure what it is any longer, except that you can build any web application you can possibly conceive with Tiki. So Tiki product management, there isn't any. As usual in open source, there's very, very little product management here. There is a shared to-do list. Anyone can add something to it. Anyone can pick up a feature and work on it. It's really a free-for-all here. Now, the interesting thing about the Tiki process is that if you can write an email and it doesn't have too many spelling mistakes, you can just ask to get access to the code repository and they may give it to you. So, in contrast to all the other processes and the process in general that we have talked about, Tiki does not jealously guide write access to the code repository, but it has a basically very positive view of people that you should be empowered, and thereby you will be motivated to do good work. Whether you're capable of doing good work or not is a different thing, but you will be given the chance to provide good work. You can actually then commit your code to the repository. Now, what happens, of course, is that basically you get a post-commit review. You commit, you break the system, a few seconds later it gets pulled because you broke the system and someone noticed. So the way my understanding is that it works is that it really lets you do things, but relying on a strong configuration management system, version control system, people do not hesitate to pull bad code that someone submitted right away. So still there are rules, and of course experienced developers and contributors will develop reasonable code so they don't break things too often. Yes, so Tiki has a monolithic software architecture in that everyone can, you can pretty much access everything and change any code. So no complex plugin architecture, but also since not every plugin isn't used, there may be bugs, but that aren't discovered anytime soon. The way the Tiki people think about it is that the higher the frequency of use, the more eyeballs there are, the faster they will find bugs. Hence, the bug count is high for highly infrequently used plugins, but nobody worries. And also for highly often used plugins, core plugins, then bugs will surface quickly. It's the common adage, Linus law, given enough eyeballs, our bugs are shallow, because there is a large community which is watching the software and identifying bugs quickly, and code gets pulled again. So that was Tiki. We will be, and that's it on these processes. I was rather quick and probably not super precise on these 3 processes because they are just too elaborate to be covered in any detail, and I just wanted to give examples. Still, in open source, in general, we can say that product management, even though ultimately it's delivering products to users in the market, there is no central control, no single responsible product manager, certainly no strategy within the project, but rather people contribute in line with their interests. They make the component work for their purposes as users of the component. A lot of the work, if anything, goes through the bug tracker as the main place where issues are managed. The engineering management process is really a collaborative process following our 3-4-5 model of open collaboration, communication, and the volunteering process. Software development is all over the place, but in general, because it's collaborative among many people, open source projects use stringent coding guidelines, and they do use their code checking tools and heuristics. In general, they try to be open source projects, try to be as slim as possible. They have low tolerance for anything that doesn't really add new functions to the project, including don't reformat stuff, don't rewrite stuff if there's no need for it from a functional perspective. Quality assurance is both different and a stronghold of open source software development because of the 2-stage or multi-stage career path where committers do quality control on any contributions by contributors using peer review and the patch submission process. And of course, they have strong community testing because well-working open source projects have strong community-based testing because of all the interests of keeping the software in good shape. So then, that's it from me for this session. We talked about how open source projects are basically components that are of how the projects are suppliers of components to their users. And it's the users and those interested in the components who contribute the most to its development. And because of that, the point of comparison is classic product development with the functions product management, engineering management, software development, and quality assurance. But when we look at it in open source projects, we will find that these 4 classic functions, as they are mapped on the 3 key roles of user, contributor, and committer, are really not done in any one-to-one fashion, but are distributed using the collaborative process that we touched upon with the 3-4-5 model and open collaboration. Finally, then, there are a few things unique to the open source process, engineering processes, in particular, again, the patch submission, the peer review-based patch submission, and inclusion process. We looked at 3 examples. These examples don't cover the whole space. They were unique in their own way. They only serve to illustrate how diverse the open source software development community is. As I mentioned early on in this course, it's let 1,000 flowers bloom, and that's why open source is such a great subject of study for new and interesting software development processes. That's it from me for now. Thank you very much, and see you in the next session. Bye.